Hello and welcome to the fourth part of my 10-part series on multivariate statistical analysis. And for this part of the series, we are going to cover multivariate repeated measures analysis. Now, multivariate repeated measures analysis is actually a very broad area of multivariate statistical analysis. And there are three data scenarios that falls under this broad umbrella. The first scenario is when we have a data set where there is one outcome of interest, and this outcome of interest has been measured repeatedly. Now, when we have this scenario, the statistical method that we would use to analyze this kind of data set is called linear mixed effect model. Now, for the second scenario, it's when we have multiple outcome variables that we're interested, but each one of them were only measured one time. And for this type of data set, we use profile analysis to analyze it. Now, for the third scenario, which is the most complicated scenario, we have multiple outcome variables that we're interested in, and all of them were measured repeatedly, measured more than one time. And the statistical method that we can use to analyze this kind of data set is called doubly multivariate repeated measures analysis. And this method is kind of a hybrid of the linear mixed effect model and the profile analysis method. Now, because multivariate repeated measures analysis is a very wide subject, I decided to divide this part of the series into 3 videos rather than just one like before. And this video, we will be focusing only on the scenario where we have one variable that we are interested as the outcome variable, and this variable has been repeatedly measured. And as I mentioned, the statistical method that we use to analyze this kind of data set is called linear mixed effect model. Now, like all statistical methods, there are always assumptions that are attached to the statistical methods in order to make the analysis that's conducted using the statistical methods valid. When it comes to multivariate repeated measures, the assumptions that we use are pretty much the same as the assumptions we would use for the MANOVA method, which I discussed in a previous video. But on top of all the assumptions that we need to follow for the MANOVA method, for multivariate repeated measures analysis, another assumption is very important, and this assumption is called the sphericity assumption. Now, sphericity, what it means is that the variance of the differences between the pairs of the repeated measures for the outcome variable, the variances must be the same between each of these pairs. So how do we test for the sphericity assumption? Now, sphericity is represented by the Greek letter epsilon for the statistical analysis. And this epsilon, what it actually represents is how much the variance of the differences between the pairs of the repeated measures, how much it deviates perfect sphericity. Now, let's say if we have perfect sphericity, the differences between each pair of the repeated measures, they would all be equal. And also in this situation, the epsilon will equal to 1. So there are 2 good ways to calculate this epsilon value, and the first method is called the Greenhouse-Geyser method. And this method is very conservative, and it tends to underestimate the sphericity value. The second good method for calculating the epsilon is called the Hun-Felt method, and this method tends to overestimate the sphericity value. So what we do in an actual analysis is we take the greenhouse geyser value as the lower bound and the Hun-Felt value as the upper bound. So we have a range. And we take this range and we see if the value 1, which is perfect sphericity, whether this value 1 is between this range. And also we look at how narrow is this interval, and the narrower the interval, the better we can argue that this data set meets the sphericity assumption. Now, so let's dive into the single outcome repeated measures analysis. Let's say we have a scenario where we want to give students 3 tests, each at a different time point, and we look at the test scores of these students at the 3 different time points. This is a situation where we have one outcome variable, which is the test score of the students. And these test scores are repeatedly measured because we gave them 3 tests, each at a different time point. Now, the question that we might ask in this scenario is that are the students' grades overall changing or not changing? So the students' grades, are they overall increasing or decreasing between the time periods of the first test and the time period of the third test? So the teacher is assuming pretty statistically savvy. So in this situation, we would first test for the sphericity of the data set to see if the test scores at the different time points, whether or not the differences between the time scores are relatively the same. And let's say if it meets the sphericity assumption, we would use the linear mix effect model to see if there is a statistically significant rising of the scores or decreasing of the scores, or if the scores between the first test and the third test are relatively similar for the students. Now, if you were to look at a data set for this scenario, the data set would probably look something like this. So we have each individual right here for each of the lines, and also for these different variables, we have the different time points for all the test scores at the different time points. And we're only interested in one variable, which is the test score. Okay, so now let's dive into our demonstration part of this video. Now, like all analyses that you might perform in the RStudio environment, the first thing you would do is to either install or open the R packages that you might need for your analysis. So I have already had my packages installed beforehand, so all I have to do is use the library function to read these packages into the environment. So the first package that I need to use is called the nonlinear mix effect package. The second one is called the reshape package. The third one is called the easy package. The fourth one is called the psych package. And the fifth one is the ggplot2 package. Now the next thing that we might do is to take the data set and read it into the RStudio environment. And what I have here is that I have the test scores for the students of a class in the form of vectors here. So I have the names of the students here, and these are the test scores for the students for test 1, the test scores for the second test, and the test scores for the third test. So what I do is I read these vectors into the R environment, and then I read the vector containing the names of the students into the environment. After that, I take the data frame function, and then I put these vectors as columns into this data frame to create the full data frame for the students' test scores for the 3 tests. Now, if we open this data frame, you will see that this data frame looks something like this, where you have the names of the students, and each test and their scores are in separate columns. Now, this might be okay if we just want to do a simple descriptive analysis or frequency analysis or something simpler than that. But if we want to do something that's very advanced, like a linear mixed effect model, we cannot be using a data set that's like this. We need a data set that's called a longitudinal data, which is in a longitudinal format. And what I mean by that, I will show you. So what I have here is that I have the melt function from the reshape package that I just read into the RStudio environment. And this function, what it does is that it takes the data set, the student data set that I just showed you before, as the first entry, and then it asks you to put in which variable is the ID variable, the variable that identifies each individual. Of course, in this case, it's the names column from the student data frame. And then the third entry for this function is the measured values entry. And how I entered it is by using a vector containing the names of the 3 columns that contains the test scores of each student. And what's being performed by this function, the result of this will be assigned the name test scores. And the result of this function is that it takes the student data frame and it gives you an equivalent of a longitudinal data frame. Now let's take a look at this test scores longitudinal data frame. What we have here is that the student test scores, they are now in 1 column instead of 3. And what we have here for these 2 columns is that for each test score, it tells you which test that it came from and which student did this test. And the 3 columns names are names, variable, which gives you the time point basically, and the value, which gives you the scores of the outcome variable that you care about. In this case, it's the test scores. So what it does, what the melt function does is that it converts a data frame like student, where the test scores are in 3 columns, into a form where the test scores are all just in 1 column, and we have 2 different columns to associate these scores to its own tests and the student names. Simple enough? So now that we have the longitudinal data frame, we can take a look at this data frame in a graph. And we do that by using the ggplot function from the ggplot2 package. So let's make this bigger so that you can see it more easily. So for this graph, you can see that the x, the horizontal axis, are the different time points, test 1, test 2, and test 3. And from here, you can see that for ggplot2, for ggplot, the first entry is the test scores data frame, and then the second entry is a combination of the aesthetics. What's the x-axis, and the x-axis is the variable column of the test scores data frame. Just to show you, so it shows the different tests. And for the y-axis, what it shows are the values, which are the test scores for each of these tests. And for group, since this is a situation where we want a separate line for each student, the group is assigned the names column, and then this is a line plot, so we put geom line right here using this function. And for the aesthetics color, each name has a different color. So as we can see from this graph, we can see with our naked eye that it seems like the students' test scores are increasing from low to high between the time points of test 1 and test 3. But is this increase statistically significant? This is the question that we need to test. We need to test using linear mixed effect models. So before we jump into linear mixed effect model, we must first perform the sphericity test to test the sphericity assumption. So we can do this by using the easy ANOVA function from the easy package. Now, for this function, the first entry, of course, it's the data frame, the longitudinal data frame test scores. And for the second entry, it's called dv, and we enter it by using dot bracket, and in the bracket, we put the name of the variable in the longitudinal data frame that contains the test scores. So the test score's name is value here. And for the third entry, it's the variable that identifies each individual in the data frame. And in this longitudinal data frame, of course, that variable is called names. So for the fourth entry, called within, what we do is we enter the column that contains the information for which time point it is. And in this case, the column name is called variable. That gives you which test was it. And for the last two entries, what you can put is detailed equal to true and type equal to 3. And we take the output of this function and we assign it to the name AOV out. So we run this line right here. And then we can just put AOV out and we run it by itself to see what's the result of the sphericity test. And this is the result of the sphericity test. Now, so for here, this is the greenhouse geyser. This is the greenhouse geyser epsilon value. It's valued at 0.995, and this value right here, it's the Hohenfeld epsilon value right here. As you can see that these values, if this is the lower bound and this is the upper bound, we would essentially have a range of the epsilon score as 0.99 to 1.28 approximately, because the Hohenfeld epsilon value is 1.276 here. Now, if we were to look at this, the value 1 is inside of this range, right? And also, this range is relatively narrow. The difference is only about 0.29. So we can argue that this data set passes the sphericity test because 1 is included in this range, and the range is relatively narrow. So now that we are done with the sphericity test, we can now move on to the linear mixed effect model. And before we do that, we apply the attach function onto the test score's longitudinal data frame. And the reason that we do this is so that in the next few analysis steps, we can now just use the names of the columns in this data frame without worrying about specifying where it came from, which data frame that it came from. And also, we apply the factor function onto the variable column of this data frame. And this is to make sure that this variable stays as a categorical variable so that it can be used as a group variable. So now let's build the linear mixed effect model, and we do that by using the linear mixed effect function from the nonlinear mixed effect models package that we just read into RStudio. And the first entry that we put into this function is a model with the outcome variable as the value column of the longitudinal data set. And this column, of course, contains the test scores of the students. And this makes sense because the outcome variable that we care about is the students' test scores. And the independent variable that influences this outcome variable is the variable column of this longitudinal data frame because it tells us which test it is. And of course, we need to specify the data set, which is called test scores right here. And the method that we're going to use, we put quote ML here, which stands for maximum likelihood. And also in this model, we do need to specify a random variable. And this variable, of course, is the names column of this longitudinal data set because for each student, they may have different scores by person for each of the tests. So this might influence the outcome score, which is the test score. But the reason that this is a random variable is because names is something that we cannot control. But this variable, which is the different time point, is something that we can control. That's why this variable is here. It's a fixed variable, and this variable here, written as tilde1 line names here, this is a random variable. Now, I'm not going to get into the idea of fixed variable and random variables here. That will need a completely different video on linear mixed effect models, which I will make in the future. But for now, let's just run this line, which builds this linear mixed effect model using this information, and the outcome is assigned the name model. So we just run this line right here. And to look at the information of this model, we use the summary function on this model. and this is the result that we get. Now, so now let's look at the results of this linear mixed effect model. And we can see the results right here. Now, we can see for this value right here, for these values represents the difference between the overall scores for the students between test 2 and test 1, the overall difference, whether or not it is significant. And these lines of values right here, they represent whether or not the difference between test 3 and test 2 for the students overall are significantly different. Now, the null hypothesis here is that for the students overall, for all 3 tests, the scores are relatively similar. So it should be that, you know, the scores didn't change between the tests for overall all the students. But whether or not we can reject this null hypothesis, we need to look at the p-value for the difference of the test score 2 with 1 and the difference of the test score 3 and 2. Now, if we were to look at the p-values here, you can see that these p-values are 0. Now, for our studio, when we have p-values that happens to be 0 here, it doesn't always equal to just plain 0. In this case, it's actually equal to a number which has many zeros after the decimal right here. So in this case, the p-values are way below the p-value of 0.05, so we can reject the null hypothesis. So what this means is that the values overall for the test scores for these 3 tests, for all the students in the class overall, they are significantly different between the tests. So now you may ask me, April, even though we deemed that the null hypothesis can be rejected, that there are differences between the scores of test 1, test 2, and test 2 and test 3 for the overall all the students in the class. Is there an increase or is there a decrease? Because the linear mixed effect model, it doesn't tell us if there is an increasing of the scores between the tests or if there's a decreasing of the scores between the tests. Now, if we actually want to see specifically if there is a gradual increase or gradual decrease of the scores, we need to look at the means of these tests specifically. So what we have here is that I applied the mean function on test 1, test 2, and test 3. Now, it's okay if you put it like this, because what this refers to is it's the vectors that I specified earlier. Now, if we were to just run these lines, we can see that for the entire class, the mean for the test 1 is 0.1, the mean for test 2 is 0.6, and the mean for test 3 is 15.3. So we can see that there is a gradual increase in the means for all the students for the test. So we can argue in an accurate way that the students, their test scores have been increasing. So the teacher in this class, he or she was probably doing a pretty good job teaching these students. So that's it for this video. And I like to take this opportunity to thank you guys for keeping up with me for this long. I know it's been 2 years since I posted my last video. I promise that I will post more videos more quickly from now on, and I hope all of you are keeping yourself healthy and safe in this COVID-19 pandemic. And thank you for listening and watching my video. And if you find this video helpful or some of my other videos helpful, please give me a thumbs up or subscribe to my channel. I really appreciate it. So see you in the next video.